In 1200 AD Baghdad, summer heat reached 120 degrees Fahrenheit, and Persian engineers had an impossible job. Cool, massive stone palaces with no electricity, no fans, no ice. The desert sun baked everything. Stone walls turned into ovens. Inside those palaces, sultans expected comfort while the outside world melted. It wasn't magic, and it wasn't luck. Persian engineers got it done using wind, water, and some seriously clever physics. Here's what cooling a palace really meant back then, and how you can build their system today for under $50. The Persian Challenge. Persian engineers aren't just building towers, they're solving physics problems that would stump modern architects. Picture this. You're standing in a stone courtyard where the ground burns through your sandals. The air shimmers with heat. Your job? Make this livable. Medieval engineers gather around clay tablets, sketching wind patterns and water flow. They understand something crucial. Moving air over water doesn't just cool things down, it transforms the entire space. Force hot air through wet surfaces under pressure, and temperatures drop 30 to 40 degrees instantly. These weren't random experiments. Persian builders spent generations perfecting what they called badger, windcatchers. Massive towers that grabbed desert wind and forced it through underground water channels. The physics was simple but brilliant. Fast-moving air over water creates rapid evaporation, and evaporation steals heat from everything around it. The secret ingredient? Surface area. Persian engineers discovered that doubling the wet surface touching the air didn't just double the cooling, it multiplied it exponentially. They used palm fiber, broken pottery, even layers of wet cloth arranged to catch every breath of air. Building the modern version. Here's what blows your mind. Everything they did, we can recreate with hardware store materials. The physics hasn't changed in 800 years. Persian engineers would recognize this build immediately, just with modern shortcuts. In 15 minutes, you'll have a working Persian cooling system. But here's what makes this even better. Once you understand how these medieval engineers thought about air and water, you can adapt their principles to cool anything, anywhere. If you're fascinated by how Persian engineers accomplished impossible cooling with just wind and water, hit that like button. This kind of practical knowledge deserves to be shared. Subscribe for more deep dives into how our ancestors mastered engineering challenges that still puzzle us today. Step-by-step build process. Step 1. Wind capture foundation. Persian engineers start every wind catcher with one crucial element: reliable wind capture. In the desert, they build massive stone towers angled at 45 degrees to catch crosswinds from any direction. We're starting with this box fan as our controlled wind source. Mount your fan securely, and I mean rock solid. Persian builders knew that unstable airflow destroys the pressure differences you need for cooling. They tested their wind towers by standing below during sandstorms. If the structure wobbled, people died. Position the fan for maximum airflow, but here's the Persian trick. They angled their wind catchers to create spinning air currents that increased cooling power by 30%. Test your airflow before proceeding. Hold your hand at arm's length. You should feel strong, steady air hitting your palm. Medieval builders spend days getting this foundation perfect because everything else depends on consistent, powerful air movement. They don't have second chances in 120-degree heat. Troubleshooting like a Persian engineer. If your fan wobbles or makes noise, it's wasting energy that should be cooling air. Secure the base. Test again. Persian engineers demanded perfect stability. Unstable airflow means people suffer. Step 2. Thermal barrier construction. Now comes the Persian engineering genius: thermal mass and insulation. In the desert, they use thick stone walls that stay cool even when the sun bakes everything else. We're recreating that principle with this styrofoam frame. Assemble your frame carefully, integrating small blocks for structural support just like Persian builders use internal stone buttresses. Watch how we seal every gap. Medieval windcatchers are airtight chambers where every cubic inch of airflow is controlled and directed. Persian engineers understand that air leaks waste 50% of your cooling power. They use clay mortar mixed with animal hair to seal joints. We're using modern materials to achieve the same airtight principle, but the physics hasn't changed. Frame-to-fan alignment is critical. Persian builders spend hours measuring angles because misaligned airflow creates dead zones where cooling stops completely. Take time to align everything precisely. Your comfort depends on getting this right. Testing frame integrity. Before proceeding, check that your frame doesn't flex under pressure. Push on stress points. Persian builders test structural integrity by having multiple people lean against their constructions. A weak frame fails when air pressure builds up. Step 3. Directional airflow channels. This panel system recreates how Persian windcatchers direct airflow through precise channels. Medieval engineers understand that chaotic airflow wastes energy. Organized airflow multiplies cooling power. Secure the first panel with 12 zip ties, following the exact pattern Persian builders use with rope and wood joints. Each connection point must be tight because air pressure drops are what make this system work. Persian engineers test their windcatchers using smoke from oil lamps to detect air leaks. Here's where Persian engineering gets clever. They don't just move air, they compress and channel it through narrowing passages. This accelerates airflow and creates low-pressure zones essential for rapid evaporation. They call it the breath of the desert. Air moving so fast it pulls heat right out of the stone. Panel positioning secret. Persian engineers discover that slight curves and airflow channels increase cooling efficiency dramatically. Don't install panels perfectly straight. Create gentle angles that guide air smoothly through the system, just like wind flowing over sand dunes. Connection technique. Pull each zip tie tight, then check again. Loose connections create air leaks that destroy cooling power. Persian builders retest every joint multiple times because precision determines whether people stay comfortable or suffer. Step 4. Evaporation surface installation. Here's where the Persian magic happens. This cooling pad replaces what desert engineers use. Layers of wet cloth, pottery fragments, and palm fiber arranged to maximize water surface area. Medieval engineers aren't just getting things wet, they're creating maximum contact between air and water. Position the cooling pad to capture every bit of airflow while ensuring complete water saturation. Persian systems use gravity-fed water from rooftop cisterns. We're using the same principle with controlled water flow. The evaporation surface area determines cooling power. Persian engineers calculate these ratios through trial and error over generations, understanding that more wet surface means exponentially more cooling. They discover that porous materials like palm fiber and broken pottery create the most efficient heat transfer. Critical placement. The cooling pad must be perfectly centered in the airflow. Persian engineers know that uneven air distribution creates hot spots where cooling fails completely. Test by feeling air movement across the entire pad surface. Every inch should have strong airflow. Saturation check. A properly wet cooling pad feels cool to the touch and shows even moisture distribution. Persian engineers test this by visual inspection and touch. You should see consistent wetness across the entire surface, like a sponge that's been wrung out but is still damp. Step 5. Structural reinforcement. Persian builders never skip reinforcement. Neither do we. Install the second panel with 4 corner zip ties placed strategically to handle the air pressure this system creates. Desert windcatchers operate under tremendous stress from wind forces and daily temperature swings. Persian engineers design joints that flex without failing, using techniques we're recreating with modern materials. They understand that rigid connections break under stress, but flexible ones last for decades. Run the fan at maximum speed and check every connection point. Persian engineers test their windcatchers during the worst sandstorms to ensure structural integrity. Your system should remain stable under maximum operational stress. No movement, no flexing, no loose connections. Stress testing. Persian builders demand that their structures handle forces beyond normal operation. They test during storms because failure during extreme conditions means death in the desert heat. Step 6. Water distribution network. The final step recreates Persian Qanat systems, the underground channels that bring water from mountain springs to desert cities. Install the water pipe with 16 precisely drilled holes, connecting the threaded adapter, coupler, and barbed end. Persian engineers understand that water flow rate determines cooling efficiency. Too fast, and water isn't absorbed by the cooling material. Too slow, and evaporation can't keep up with airflow. They achieve perfect balance through careful observation and adjustments over multiple seasons. Watch what happens when we add water. The physics changes completely. Secure the entire water system to the frame with zip ties, ensuring even distribution across the cooling pad. Persian builders use mathematical spacing to achieve perfect coverage. Uneven distribution creates dry spots where cooling fails. Water flow calibration. Start with low flow and gradually increase until the cooling pad stays saturated but doesn't drip excessively. Persian engineers achieve this balance through generations of testing. The pad should feel like a wrung-out sponge, damp throughout but not soaking. Final system integration. With water flowing and fan running, check that every component works together smoothly. Persian engineers test complete systems extensively before declaring construction finished. If water pools anywhere or airflow seems restricted, adjust components until the system operates with perfect efficiency. Testing the Persian physics. Room temperature baseline, 85 degrees Fahrenheit. Now watch this temperature drop in real time as we activate the same physics Persian engineers used 800 years ago. The thermometer drops immediately as evaporation begins, just like it did in Baghdad palaces. Persian windcatchers drop temperatures by 15 to 20 degrees within 30 minutes of operation. Our modern version achieves the same cooling using 20 watts of electricity for the fan. Persian engineers did it with zero electricity, just wind and gravity-fed water. Real-time measurement. Watch the temperature drop happen in stages. First, a quick 5-degree drop as evaporation begins, then steady cooling as the system reaches optimal efficiency. Persian engineers observe these same patterns and use them to optimize their windcatcher designs. Air quality improvement. As temperature drops, notice how the air quality improves. The system adds beneficial humidity while cooling. Persian engineers design cooling that enhances health rather than compromising it. Modern AC systems dry air and can cause respiratory problems. Operating efficiency. This system runs for hours without degradation. Persian windcatchers function for decades with minimal maintenance. The simple physics and robust construction mean reliability that complex modern systems can't match. Climate testing. Persian engineers develop variations for different humidity conditions. Below 60% humidity, evaporative cooling performs excellently. Between 60–70%, it still provides significant cooling. Above 70%, effectiveness decreases, but those are exactly the conditions where Persian engineers develop alternative techniques. Modern applications of ancient wisdom. This system works anywhere with humidity below 60%, covering most of the continental United States during summer. For emergency cooling during power outages, this Persian technology could be life-saving. Persian principles scale perfectly. Off-grid cabins, workshops, greenhouses, even outdoor patios become comfortable spaces. Modern architects are incorporating these desert engineering principles into billion-dollar buildings because the physics is undeniable. Regional adaptations. Egyptian builders use multiple towers with cross-ventilation. Spanish engineers combine evaporative cooling with thermal mass that stores coolness overnight. Indian architects develop courtyard systems that create convection currents, pulling cool air through living spaces. Advanced techniques. Persian engineers develop dual-stage cooling systems. Adding ice to the water reservoir drops temperatures an additional 9 to 14 degrees Fahrenheit, creating Arctic-level cooling in desert climates. Urban applications. For apartment dwellers, smaller versions using desk fans achieve significant room cooling. The physics scales down perfectly. Persian chambers use miniature windcatcher principles for personal cooling in small spaces. Despite operating in 120-degree desert heat with no electricity, no modern materials, and no backup systems, Persian engineers managed to cool massive stone palaces to comfortable temperatures. The windcatchers weren't just functional, they were engineering marvels that operated reliably for centuries. Even more impressive were the people who managed to build entire civilizations in landscapes that would challenge modern technology. Persian cities thrived in conditions that would shut down our electrical grid. If this exploration of Persian cooling engineering amazed you, subscribe for more deep dives into practical skills our ancestors mastered. What aspect of windcatcher design impressed you most? Share your thoughts below, and stay cool the Persian way. Next week, how medieval households preserved fresh meat for months without refrigeration using techniques that work better than modern methods. The science will amaze you.